Hi, I'm Antonio Sala, and in this video we are going to model this pinion and rack mechanism in order to compute the accelerations that happens a consequence of somebody pushing with some force F in here and somebody else exerting a torque tau in this rotation axis. We will assume that the rotation axis is fixed, as well as the green element, so that only rotation of the red pinion and horizontal movement of the rack element must be considered. Also, well, this shape of the teeth is this way because contact may happen at different places as this pinion rotates, but well, we will disregard that nuances in our model and we will just consider that contact takes place at a fixed distance rho from the center of rotation. So when contact is here or whatever, we will just forget about that and assume that this is, sort of a cylinder touching a plane. Good. In this first video, we will model the mechanism using Newton equations. Mass times acceleration equal force balance, or if we are considering rotation, moment of inertia times angular acceleration equal resulting torque. So let's discuss which equations can we write for this system, and the first we are going to write is the kinematics, let's say, the mechanical constraint, saying that if we denote the angle of rotation θ1 and we denote as q2 the horizontal displacement of the green element, then we observe that the mechanical construction is such that q2 is θ1 times the radius rho. Of course, this equation can be equivalently written as this kinematic constraint in velocities, but okay, they are the same except for integration constants when going from velocities to positions. But as integration constants are sort of what we consider to be zero in our reference system, then we will consider these two equations to be the same, let's say. And also, if we take another derivative, we are also able to write it in acceleration units if needed. In fact, the one we are going to use is this in the accelerations, because in the force balances, the things that actually do appear are accelerations, not positions and speeds. More on that later. Okay, nevertheless, let us write Newton equations for body 1, which is that moment of inertia times angular acceleration is equal to resulting torque. So if somebody exerts a torque tau in the rotation axis, I will have it, but well, what happens with the interaction between the green and red bodies? Well, there will be a reaction force, so that if somebody exerts tau, it will push towards the right hand side the green body with a force R at the contact point, and conversely, in the torque balance, the opposite reaction force will be how the green body pushes the red one. And of course, we will only be interested in the horizontal components of this reaction force, even if contact is at an angle, this kind of gear stuff. I'm not a mechanical engineer for the details. So the horizontal component of this reaction force will produce a torque, force by distance to the rotation axis minus reaction force times radius. Good. If we now write down the Newton equations for the body 2, for the green body, then we'll have mass times acceleration equal to resulting force, which will be, if positive is movement to the right hand side, this force arrow points left, so we will put minus F, and then reaction force will push right, at least in the drawing we are doing. Note that when we are modeling dynamic systems, these signals change in time. So if R gives a negative value, means that because of the laws of physics, the gear is pushing the green body in the leftwise direction. So R can be positive or negative. This is just a convention on how we write the arrows in here. So good. The thing is that we already have all the mechanical equations we need. This will be equation 1, this will be equation 2, and I will call any of the three versions of the same stuff as equation 3. Why is the model complete? Well, because we have lots of letters, F, tau, theta 1, Q2, and the reaction force R, but if we consider this to be inputs that can take any arbitrary value, I can push my axis or my green body with whatever force I wish, then these three signals will be unknowns, and if I have three equations and three unknowns, my mathematical model of this physical system is complete. So this is it. Physics ends here. The remaining thing is just manipulating these equations to solve for the variable we wish or to express them in whatever form we wish to. So for instance, as this mechanical system has what is say 1 degree of freedom, because if I know the rotated angle, then with these equations I can immediately multiply by rho and tell the green object's movement, then Q2 and theta 1 are proportional, so it's customary to try to eliminate from the equations either Q2 or theta 1, and also we'll try to eliminate the reaction force. As I said, this is just a standard way that mechanical engineers are used to write the equations, but from the mathematical point of view, these three equations, three unknowns, is already a perfectly valid way of writing the model that can be solved for. But let's manipulate it. Then we will first try to eliminate Q2 and R. How can we do that? Well, as only accelerations appear here, we will sort of use this version of equation 3, and I will use that to replace this acceleration by rho times acceleration 1. So equations 2 and 3 end up saying this, and now in order to eliminate the reaction force, if I multiply by rho both sides of the inequality, then I get plus r rho, and here I have minus r rho. So if I sum equation 1 to these equations 2 plus 3, then I get, summing right hand side and left hand side of the equations, moment of inertia plus m rho squared times acceleration equal to r rho vanishes, and I get tau minus f rho. So this is what is called the equivalent mechanical model as viewed from the rotation side, from the red body. So this is the equivalent moment of inertia because it's what multiplies acceleration. But in control, for instance, we are used in writing this in normalized form. So instead of a second order derivative, we'll express it as two first order differential equations, as say that the derivative of the angular position, I will call it angular speed omega, and the derivative of the angular speed is 1 over the equivalent moment of inertia times the equivalent resultant torque, which is tau minus f rho. And this is a perfectly solvable system of ordinary differential equations with two inputs, tau and f, and two states, angular position and angular speed. So this will be the state equations and output equations. As I have three unknowns, I need to solve for Q2 and R. Solving for Q2 is trivial. Q2 is the radius times theta 1. And which is the reaction force? Well, the reaction force, as I have eliminated it, I need to do some work again. If I move down, the original equation with the reaction force was this thing, so basically the reaction force is equal to 1 divided the radius. But okay, the equation of the angular acceleration in the overall model, I just deduced that it was this one, so this will be the expression of the reaction force as a function of constant parameters and inputs. So if do a little bit of cleanup, it will be this expression involving f and tau. I divide by rho to have sort of force equivalent expressions, so this is kind of a convex combination of the inertia and the m rho squared. Well, the thing is that this will be the reaction force, if we are interested in it for whatever purpose. In equilibrium, if acceleration is zero, the reaction force is just equal to the applied force, of course, because the green object must not move. But, as you can see, if there is an acceleration, the reaction force cannot be equal to F, because if that were the case, acceleration would be zero. In that second case, then we get this expression for the reaction force. Good. If we now quickly do the reduction to the linear movement, to eliminating theta 1 and reaction force, then I will replace equation 3 in 1 to get this, and then as I am looking to eliminate reaction force, I will divide by rho both sides, so that when I add up these two equations, I will get this final equation in which only the acceleration of the green object is the unknown. So this thing here will be the so-called equivalent mass, because it's what multiplies to the linear acceleration of the green body. Then the green body feels the torque divided by the radius, and somehow the overall mass and inertia combine so that this overall system acts as if it were a single green body with a little more mass, adding moment of inertia divided by square radius. Then, of course, we would be able to write a similar set of state equations in normalized form, and if I solve for Q2, then divided by radius, I will get theta 1, that's easy, and with similar manipulations we did earlier on, we should be able to obtain exactly the same expression for the reaction force. For brevity, I leave all that to you. So we end the video here, summarizing in that in this mechanical system there is only one degree of freedom, so we can express it as seen by the rotational side or as seen by the green translational side. Both expressions are equivalent. In the former case, we had an equivalent moment of inertia, I plus m rho squared. In the latter case, we had an equivalent mass, m plus inertia divided by rho squared. Reaction force is eliminated from the equations, but with some manipulations, of course, it can be computed. So we end the video here. Thanks for watching.